Tonight, go outside and look up at the sky. If you're away from city lights, you'll see stars, hundreds of them, maybe thousands, scattered across the black, and between them, darkness, a lot of darkness. That's what the sky looks like. That's what it's always looked like. It seems completely ordinary. It seems like it shouldn't require any explanation at all, though most people overlook it. The darkness is the mystery, not the stars. The darkness. Think about what's actually up there. Our galaxy alone contains somewhere between 100 and 400 billion stars. That's just the Milky Way. Beyond it, there are at least 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars of their own. When you add all of that up, you're looking at something in the range of 2 septillion stars. That's a 2 followed by 24 zeros. 2 septillion individual suns, burning, radiating energy in every direction, pouring light into the universe on a scale our brains are not really equipped to process. And yet, you look up at the sky, and most of what you see is black. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. That should bother you. Think about it for a moment. If you're standing in a forest dense enough, every direction you look eventually hits a tree. You can't see through the forest because wherever your eye travels, a trunk or a branch stops it. Now imagine a universe that goes on forever, filled in every direction with stars. You look left, your line of sight eventually hits a star. You look up, down, any angle at all. Every single direction terminates on the glowing surface of some star somewhere out in space. If the universe is infinite and filled with stars, the math says the entire night sky should be as bright as the surface of the sun. Not just bright with a few pinpoints of light, uniformly, blindingly, completely bright. Every bit of it, every direction. Day and night, the sky should blaze. That's not a poetic exaggeration. That's what the geometry actually predicts. And instead, you go outside on a clear night, and it's dark. Most of the sky is just black. People have been troubled by this for a very long time. This isn't a modern puzzle that only emerged after telescopes. As far back as the 1500s, thinkers were already noticing the contradiction. Thomas Digges, an English astronomer, wrestled with it. Johannes Kepler thought about it. Edmund Halley, the same Halley the comet is named for, considered it seriously. Jean-Philippe de Chezeaux worked through the numbers in the 1700s and couldn't make them add up. For centuries, careful observers kept arriving at the same uncomfortable question. If the universe is full of stars, why is the night sky dark? Nobody had a satisfying answer. The question just kept resurfacing, generation after generation, because it refused to go away. And the reason it refused to go away is that it's not a small question. The darkness of the night sky isn't a minor aesthetic detail. It's telling you something. Something about the size of the universe. Something about how old it is. Something about whether it had a beginning. Every time someone looked up at the dark sky and felt that nagging sense that something didn't add up, they were touching the edge of a much deeper truth about the structure of reality. They just didn't know it yet. Now, several explanations get proposed when people first think about this. Maybe there's dust and gas between the stars, blocking the light. Maybe the stars aren't spread evenly through space. Maybe the universe has edges, and beyond those edges there are no more stars. These all sound reasonable. They all fail, and they fail in ways that are genuinely instructive, in ways that push you toward the real answer. That process of elimination matters because the actual explanation isn't one that anyone would reach by intuition alone. It requires knowing something that humans didn't discover until the 20th century. The resolution to this paradox reaches into some of the most profound physics we've ever uncovered. It involves the speed of light. It involves the age of the universe. It involves the fact that space itself is not sitting still, that it has been expanding since the beginning, stretching the light from distant stars into forms our eyes can't detect. It involves the limits of human vision and what we're actually capable of seeing versus what the universe is actually filled with. Each piece of the answer reveals something new about where we are, when we are, and what kind of universe we're living in. The answer is not simple, it's layered. And each layer, when you understand it, changes how you see the sky, not just at night, but in general. Because what the night sky is showing you, it turns out, is a snapshot of cosmic history. A record written in light and darkness of everything that has happened since the very beginning. The darkness of the night sky isn't just background scenery. It turns out to be one of the most important clues we have about the nature of the universe itself. The paradox has a name, Olbers Paradox, after the German astronomer Heinrich Wilhelm Olbers, who wrote about it in 1823. But here's what most people don't realize. Olbers didn't discover the problem, he inherited it. Johannes Kepler wrestled with it in the early 1600s. Edmund Halley brought it up in the 1700s. A Swiss astronomer named Jean-Philippe de Chasseau worked through the mathematics decades before Olbers put his name anywhere near it. The question had been floating around for centuries, passed from one careful thinker to the next, and none of them could put it to rest. We call it Olbers Paradox today, mostly out of habit. The name stuck. But the confusion is much older than one German astronomer writing one paper in 1823. So, what is the paradox exactly? It starts with an assumption that seemed completely reasonable at the time. The universe is infinite. It goes on forever in every direction, and it's filled with stars, more or less uniformly, spread throughout that infinite space. If both of those things are true, something strange follows, something that seems almost undeniable once you work through it, something that directly contradicts what you see every time you look up at a dark night sky. Think about standing in a forest, a dense forest, trees packed tightly in every direction, stretching out as far as you can go. If you pick any direction and look, your line of sight is going to hit a tree, maybe a close one, maybe a distant one. But somewhere along that line, a tree is there. It doesn't matter which way you turn. Every direction ends at bark. That's what a dense, large enough forest does to every line of sight you have. It fills them all. Now replace the trees with stars. If the universe is infinite and stars are spread throughout it, the same logic applies. Pick any direction at all. Look along that line as far as it goes. In an infinite universe packed with stars, that line has to eventually hit a star. Every single line of sight terminates on a stellar surface. Not some of them, all of them. There are no gaps in an infinite, uniformly filled universe. Every direction ends at a star, and here's where it gets strange. Here's where the math stops feeling abstract and starts feeling alarming. The surface of a star is extraordinarily bright. Our own sun, a perfectly average star by cosmic standards, has a surface temperature of around 10,000 degrees Fahrenheit. That surface blazes with light. Now imagine that every point in the sky, every possible direction you could look, ends at a surface like that. Not just a handful of stars, not just a bright band of the Milky Way. Every single point. The entire sky in every direction should be as bright as the surface of a star. Think about what that means. Not a few bright stars against a dark background. A sky so blindingly brilliant that it would make noon on a summer day look dim by comparison. The whole dome above you, from horizon to horizon, glowing with the intensity of a stellar surface. No dark patches, no empty space between the points of light, just an unbroken wall of light in every direction, day and night, forever. That is what the math predicts. That is what an infinite, eternal, uniformly filled universe should look like from the inside. And yet you can walk outside tonight and see darkness. Stars scattered across a black sky, gaps everywhere. The prediction and the observation don't match. That mismatch is Olbers' Paradox. Olbers understood it this clearly when he wrote it up in 1823. So did Kepler 2 centuries before him. Kepler actually used the dark night sky as an argument that the universe couldn't be infinite. If it were infinite, he reasoned, the sky would blaze. It doesn't blaze. So the universe must have an edge, some boundary beyond which the stars stop. It was a logical response to a genuine problem. But it didn't fully satisfy anyone, and it raised more questions than it settled. De Chazot tried a different approach. He worked through the numbers more carefully. He calculated how the brightness of stars should add up across larger and larger distances, even accounting for how stars get dimmer with distance. In a truly infinite universe, the contributions from ever more distant stars should compensate. More stars, farther out, filling in every gap. The total light reaching your eye should build up to something enormous. His math confirmed the paradox instead of dissolving it. What makes the paradox so stubbornly difficult is how clean the logic is. There aren't many assumptions buried in it. You need the universe to be infinite. You need it to be uniformly filled with stars. You need light to travel freely through space without disappearing. Those all seemed like reasonable starting points, and from those starting points the conclusion is almost unavoidable. Every line of sight hits a star. Every point in the sky glows. The night should be as bright as the surface of the sun. You can poke at individual steps in the reasoning, but the core argument keeps holding together. What made Olbers' paradox so philosophically unsettling wasn't just the mathematical contradiction itself. It forced astronomers to confront the very nature of the universe at the largest scales. The problem couldn't be dismissed as a minor observational quirk or a measurement failure. It was, in essence, a conflict between first principles and plain experience. If your logical reasoning from basic assumptions leads to a prediction that contradicts what you directly observe, something fundamental must be wrong with either your assumptions or your understanding of nature. This made the paradox far more than a puzzle to solve. It was a crisis point in cosmological thinking. For centuries, the best minds in astronomy and mathematics couldn't find a comfortable resolution. The dark sky remained obstinately dark, while the reasoning remained obstinately sound. Astronomers and mathematicians spent a long time looking for a flaw. Maybe stars aren't perfectly uniform in their distribution. Maybe light gets absorbed somehow as it travels. Maybe the universe has some structure at large scales that changes the calculation. Every proposed escape hatch got examined. Every one of them ran into new problems. The paradox didn't go away just because you wanted it to. The dark night sky remained dark. The logic remained sound, and the gap between prediction and observation stayed wide open. For a very long time, nobody had a satisfying answer. The first explanation most people reach for is dust. It makes intuitive sense. Space isn't perfectly empty. There are clouds of gas and dust drifting between the stars, and if something is blocking the light, maybe that's your answer. Maybe the dust is simply absorbing all that starlight before it reaches us. It sounds reasonable. It feels like it should work. But it doesn't. Here's the problem. Dust isn't a sponge that swallows energy and holds it forever. When a dust cloud absorbs radiation, that energy has to go somewhere. It heats the dust gets warmer, and a warm object radiates heat. It emits light of its own, just at a different wavelength than the starlight it originally absorbed. You haven't removed the energy from the equation, you've just changed its form. The dust cloud absorbs visible light from distant stars and re-emits that energy as infrared radiation. The sky you thought you were darkening is still full of light. It's just light your eyes can't see as easily. But the energy is there, all of it. You haven't solved the paradox. You've only delayed it by a fraction of a second and shifted the wavelength slightly. And if the universe were truly infinite and packed with stars, those dust clouds would absorb so much radiation over so much time that they'd eventually heat up to the same temperature as a stellar surface. They'd glow just as brightly as the stars they were supposed to hide. You'd still end up with a sky blazing in every direction. Every direction you look, something is radiating. The dust solution doesn't darken the sky. It just changes what's doing the glowing. So dust is out. What else did people try? The next idea was this. Maybe the universe simply isn't infinite. Maybe it has an edge, a boundary, some finite limit to how far it extends. If that's the case, then there are a finite number of stars. And if there are a finite number of stars, then maybe there just aren't enough of them to fill every line of sight. The sky is dark because there's empty space beyond the outermost stars. And when you look in certain directions, you're looking past all of them, into a void with nothing in it. This sounds more promising, and there's something philosophically appealing about it. It trades an infinite universe for a bounded one and avoids the math that leads to a blindingly bright sky. But when you press on it, problems appear. The argument only works if the universe is not just finite, but also young enough that the stars haven't had time to fill the sky with light. A universe with edges, but billions upon billions of years of accumulated starlight, could still, in principle, produce a bright sky. All those finite stars, burning for long enough, would collectively illuminate every line of sight. The geometry changes, but the energy doesn't disappear. Think about what it would actually require. You'd need a universe finite enough, and with stars young enough, that the total accumulated light output across all of time simply hasn't added up to a bright sky yet. And if you're already leaning on the age of the universe and the youth of the stars to make the numbers work, you're already reaching for the real answer without knowing it. The finite boundary alone doesn't save you. And there's another problem. Even if the universe has edges in space, those edges are so far away, and the stars between here and there are so numerous, that a simple boundary doesn't cleanly resolve anything. You still have to explain why the stars that do exist, given enough time, haven't collectively lit up the night. A finite universe is only a partial answer at best, and it raises as many questions as it settles. The third idea involves the distribution of stars. Maybe stars aren't spread uniformly through space. Maybe they clump together in galaxies, and those galaxies cluster in groups, and those groups cluster into superclusters, with vast dark voids between them. If the universe is lumpy rather than smooth, maybe the dark patches in the sky correspond to those voids. You're looking between the clusters. There are no stars there, so it's dark. This idea captures something real about the universe. Stars do cluster into galaxies. Galaxies do cluster into groups and superclusters. The large-scale structure of the universe is genuinely clumpy, with enormous filaments of matter surrounding vast bubbles of relative emptiness. So the observation is correct, but the conclusion doesn't follow. Here's why. If you zoom out far enough, the universe looks smooth. At the largest scales we can observe, the The distribution of matter is roughly uniform. There are voids, yes, but there are also walls of galaxies, sheets of galaxies, immense concentrations of luminous matter. If you average over a large enough region, the density evens out, and in an infinite universe with an uneven but statistically uniform distribution of stars, the clumpiness doesn't solve the problem. You've moved the dark voids around, but the total amount of starlight hitting any given point in space adds up the same way it always did. The geometry of clustering doesn't remove the light, it just rearranges it. There's also this: the gaps between clusters of stars are themselves enormous, spanning millions of light years in some cases. But the stars on the far side of those voids are still there. Their light still travels. An infinite universe with gaps in it is still an infinite universe. The light from stars beyond the gaps is still coming. In an infinitely old static universe, all of that light would have had infinite time to cross even the largest voids. The clumping of stars delays the arrival of light from certain directions. It doesn't prevent it from arriving. So none of these explanations actually work. Not the dust, not the boundary, not the clustering. Each one makes a move that seems logical at first, and each one falls apart when you examine it carefully. Dust radiates. A finite universe needs extra assumptions to darken the sky. Clustering doesn't reduce the total light. Every attempted solution keeps running into the same wall. If there are enough stars, and they've been burning long enough, in a universe old enough and large enough, the light should be everywhere. What that tells you is that the real answer isn't about the arrangement of stars at all. It isn't about what's between them or how they're grouped. It's about something more fundamental. Something about time. Something about the nature of the universe itself, not just the objects inside it. The proposed solutions all try to rearrange the furniture without asking whether the room is the right shape. And that turns out to be exactly the wrong approach. The real answer wouldn't come until the 20th century. And when it didn't just explain why the sky is dark. It revealed something fundamental about the structure and history of the universe. Here is the key piece of information that changes everything. The universe has an age. It isn't eternal. It didn't always exist. Roughly 13.8 billion years ago, the universe began. And that single fact, more than anything else, is what explains the darkness of the night sky. Not dust, not uneven clustering, not the gaps between galaxies. The answer was hiding in something much more fundamental. Time itself. Light travels fast, almost incomprehensibly fast, about 186,000 miles every second. In 1 second, a beam of light could circle Earth 7.5 times. In 8 minutes, it crosses the entire distance from the sun to your eyes. In 4 years, it reaches our nearest neighboring star. These are staggering speeds by any human standard. But here's what most people don't stop to consider. Speed only matters when you also have distance. And when the distances involved are cosmic, even light, the fastest thing in the universe, takes time to arrive. Think about what that means. If a star is 1 billion light years away, the light leaving it today won't reach Earth for 1 billion years. We won't see that light. Our descendants won't see that light. Nobody alive in any civilization we can currently imagine will see that light. It simply hasn't arrived yet. It's out there, crossing the void, photon by photon, covering 186,000 miles every second. But 1 billion light years is a long way, and time is not infinite. The universe is only 13.8 billion years old. That puts a hard limit on everything. There is a sphere around Earth. Astronomers call it the observable universe. Everything inside that sphere is close enough that its light has had time to reach us since the universe began. Everything outside that sphere hasn't sent us anything we can detect, not because it's empty, not because the stars out there aren't shining, but because their light left too recently or too far away, and it simply hasn't crossed enough space to arrive. The edge of that sphere sits at roughly 13.8 billion light-years in terms of light travel time. That's the boundary, that's the wall. And beyond it, the sky goes dark. This is the resolution to Olbers Paradox that centuries of astronomers couldn't find. The paradox assumed an infinitely old universe. It assumed light from every star in every direction had always been traveling and had therefore already arrived. But that assumption was wrong. The universe had a beginning, and a beginning means that light from distant sources is still in transit, right now. As you're watching this, somewhere out there, light from a star or galaxy that formed early in cosmic history is crossing space, gradually closing the distance to Earth, and it won't arrive for millions or billions of years more. When it does, someone or something might detect it. But today, that direction in the sky looks dark. The most distant objects we've ever detected sit at the very edge of the observable universe. The light arriving from them right now left its source more than 13 billion years ago. When that light began its journey, the universe was young. Stars were still forming for the first time. There were no planets. There was no Earth. There was no solar system. Whatever process eventually produced our sun hadn't happened yet. That ancient light has been crossing space for longer than the Earth has existed, longer than the sun has burned. It's been traveling since before anything we'd recognize as a world was possible. And here's what makes this genuinely eerie. The objects that produced that light may no longer look the same. They've had 13 billion years to evolve while the light was in transit. We're seeing a snapshot of something ancient. The universe we observe is not the universe as it currently exists. It's the universe as it was at different moments in the past, with distant objects showing us more ancient versions of themselves. The further away something is, the further back in time we're looking. It's a cosmic time machine, and we didn't build it. We're just receivers. When astronomers observe the universe, they're not seeing a single moment frozen in time. They're seeing a temporal cross-section built across billions of years. Light from nearby stars shows us the universe from just decades ago. Light from distant galaxies reveals the state of the cosmos millions of years in the past. This layering of observations means that our view of the universe contains built-in information about how the cosmos has changed and evolved over cosmic history. We can literally watch evolution unfold simply by looking deeper into space. The universe has written its own history across the sky for us to read. Now consider the dark patches. The gaps between stars, between galaxies, between the faint smudges of light at the edge of our deepest images. Those aren't voids. They're not regions where the universe simply forgot to put anything. In many cases, there are objects out there, stars, galaxies, perhaps entire clusters of galaxies, that are either too far away or too young in their light travel time for their photons to have reached us yet. We're not looking at absence. We're looking at a clock that hasn't finished counting down. The darkness is future light, light that hasn't arrived. Some of those dark patches do contain sources that are genuinely beyond our reach, beyond the observable horizon. But even within our observable universe, the finite speed of light and finite age of the cosmos mean that plenty of objects are still dark to us simply because their light is still traveling. If you could somehow accelerate time forward, you'd watch those dark regions slowly begin to glow as new light arrived from sources that were previously too far away or whose light was only now completing its journey. Let's put a number on this to make it feel real. The observable universe contains roughly 2 trillion galaxies within the sphere we can detect. 2 trillion. Each galaxy holds hundreds of billions of stars on average. The numbers are genuinely beyond what our minds can process. And yet, for all of those sources of light, the night sky between them is dark. The finite age of the universe means we only receive a fraction of the total light those sources have ever produced. The rest is still traveling. The rest hasn't arrived. The universe started 13.8 billion years ago, and 13.8 billion years, while enormous by human standards, is a finite slice of what would be required to fill the sky with light from every possible direction. There's something almost uncomfortable about sitting with this idea. You look up at a dark patch of sky. You might assume nothing is there, but the darkness doesn't mean nothing. It means time. It means that somewhere out there, something exists, has perhaps existed for billions of years, producing light that has crossed an unimaginable gulf of space and simply hasn't reached your eyes yet. You're not looking at emptiness. You're looking at a gap in your light cone, the boundary of what the universe's age has permitted you to see. The photons meant for that moment in your sky haven't arrived. They may arrive in 1 billion years. They may arrive in 10 billion. But right now, that patch of sky looks black, not because the universe placed nothing there, but because the universe isn't old enough yet for the light to have made the trip. This is what a finite-aged universe actually looks like from the inside. This is the view from Earth, 13.8 billion years in. We sit inside a bubble of received light, surrounded on all sides by a darkness that isn't empty. It's delayed. It's the universe's past, still traveling toward us. It's photons in flight across distances that dwarf anything in our experience. It's the evidence, written in shadow, that the cosmos began at a specific moment, and that specific moment was close enough in time that the light from the far edges of what's out there hasn't had a chance to reach us. In those dark patches between stars, you're not looking at nothing. You're looking at distances so vast that the light from whatever is out there hasn't finished its journey yet. But the finite age of the universe is only part of the answer. The universe isn't just old. It isn't just finite. It's moving. Right now, as you read this, galaxies are rushing away from each other in every direction. Not because they're flying through space the way a rocket flies through air. Space itself is expanding. The fabric of the universe is stretching, carrying galaxies along with it, the way dots on a balloon move apart when you inflate it. And the farther away a galaxy is, the faster it's receding. That's not an intuition. That's an observation. Astronomers have confirmed it repeatedly across decades of measurement, using multiple independent methods. Now here's what that means for light. When a galaxy is racing away from you and it sends out a light wave, that wave gets stretched as it travels. Think about what's happening physically. The light leaves the galaxy at a certain wavelength, but while it's in transit, the space it's traveling through is expanding. The wave gets pulled, it elongates. By the time it arrives at your eye, it's longer than when it started. A longer wavelength means a redder color. This is what astronomers call cosmological redshift, and it's one of the most important ideas in all of modern science. The key distinction here is crucial. Redshift from expansion differs fundamentally from the Doppler effect you experience with sound. When a train whistles as it approaches, the sound waves compress, making the pitch higher. When it recedes, they stretch, making the pitch lower. That's the Doppler effect, and it occurs in a fixed background. But cosmological redshift isn't about motion through space. It's about space itself changing. The wavelengths are expanding because the geometry of the universe is expanding. There's no absolute reference frame from which the galaxy is moving away. What matters is that the distance between us and the galaxy is increasing. and that increase is stretching every light wave in transit. Visible light runs from violet at one end to red at the other. Violet wavelengths are short, red wavelengths are longer. When expansion stretches a light wave beyond the red end of the visible spectrum, it shifts into infrared. Our eyes cannot see infrared. Stretch it further and it becomes microwave radiation. Our eyes cannot see that either. Stretch it further still and it becomes radio waves. None of this is visible to us without specialized instruments. So here's the problem. Even if the light from a distant galaxy has successfully completed its journey across billions of light years and actually arrived at Earth, that doesn't mean we can see it. If expansion has stretched the wavelength beyond the visible range, the light passes right through our eyes without registering. It's here. It's real. We just can't detect it. This is not a small correction to the problem. This is a second major mechanism actively hiding the universe from us. The finite age limits how much light has had time to arrive. Redshift hides a large fraction of the light that has arrived. Both are working simultaneously. Both push toward the same result, a dark sky. Let's talk about numbers for a moment, because the scale of this redshifting is staggering. A galaxy roughly 4 billion light-years away has its light shifted noticeably toward the red end of the spectrum. A galaxy 10 billion light-years away has its light shifted dramatically. By the time you're looking at the most distant galaxies detectable with modern telescopes, the light they originally emitted as ultraviolet radiation has been stretched all the way into the infrared. What started as high-energy, short-wavelength light has been pulled into a completely different region of the electromagnetic spectrum. The galaxy is still there. The photons are still arriving, but they're invisible to the naked eye. Here's what most people don't realize. This isn't a rare edge case affecting only the most distant objects. Redshift affects essentially everything beyond our local neighborhood. The farther you look, the more severe the effect. And because the universe is vast, most of the galaxies out there are far away. Most of their light is shifted. Most of it is arriving in forms our eyes can't process. Consider the implications. We live in a universe teeming with billions of galaxies, yet the vast majority of their light reaches Earth in wavelengths completely invisible to human vision. This isn't a limitation of our instruments. It's not a failure of our telescopes. It's a consequence of the expansion of space itself. The universe could be blazing with visible light, and we would only perceive a fraction of it. The redshift takes light from the part of the spectrum our eyes evolved to see and redistributes it across wavelengths we cannot perceive. The most dramatic example of this is the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form for the first time. Before that moment, space was filled with a dense, hot plasma. Light couldn't travel freely. It was constantly scattering off free electrons, bouncing around without getting anywhere. When atoms finally formed, the plasma cleared. Light was released. It flooded through space in every direction. And that light, at the moment of its release, was as bright and as hot as the surface of a star. Every point in space, in every direction, was glowing with that intensity. Not a few bright spots scattered across a dark sky. Everything, everywhere. That was 13.8 billion years ago. Since then, the universe has expanded by a factor of roughly 1,000, and those light waves have been stretched along with it. A factor of 1,000 in expansion means the wavelengths are now about 1,000 times longer than they were. Light that was originally emitted as brilliant high-energy radiation has been pulled into the microwave portion of the spectrum. Today, that ancient light still fills all of space. It's everywhere right now. It's passing through you as you watch this. It's passing through the walls of whatever building you're in. It permeates the entire observable universe at a temperature of about 2.73 degrees above absolute zero. But you can't see it. Your eyes are not sensitive to microwaves. The most spectacular light show in the history of the universe is happening all around you, and your visual system registers nothing. If human eyes could detect microwaves, the night sky would glow uniformly in every direction. There would be no dark patches. The entire celestial sphere would shine. But we can't see microwaves, so instead we look up and see black. Radio astronomers first detected the cosmic microwave background in 1965. Arno Penzias and Robert Wilson were using a large horn antenna in New Jersey. They kept picking up a persistent background noise that came from every direction equally. They tried everything to eliminate it. They assumed it was interference. They cleaned the antenna. They checked their equipment repeatedly. The signal wouldn't go away. It was coming from the sky itself. What they had stumbled onto was the remnant glow of the Big Bang, stretched by 13.8 billion years of cosmic expansion into microwave radiation. They eventually won a Nobel Prize for the discovery. The signal they detected was the ancient light of the early universe, rendered completely invisible to human eyes by the very expansion that solved Olbers Paradox. Now think about what this means for every other distant galaxy. If the cosmic microwave background has been stretched that severely over 13.8 billion years, then light from galaxies formed in the early universe has also been dramatically shifted. Galaxies that formed a few hundred million years after the Big Bang were emitting visible and ultraviolet light when they were young and intensely star-forming. By the time that light reaches us, after traveling across more than 13 billion light-years of expanding space, it arrives as infrared radiation. The galaxies are real. Their light has reached us. We simply cannot see it with our eyes. This is where modern astronomy steps in. Infrared telescopes can detect what our eyes cannot. The Hubble Space Telescope, operating primarily in visible and near-infrared wavelengths, has pushed the boundary of what we can observe. It revealed galaxies so distant and so redshifted that they were completely invisible in earlier surveys. But even Hubble had limits. The most distant galaxies, those whose light has been stretched the furthest, were still beyond its reach. The James Webb Space Telescope was built precisely to see this shifted light, detecting galaxies whose light has been stretched so far into the infrared that no human eye could ever find them. There is another way to think about this, and it starts with the human eye. The human eye is an extraordinary instrument. It can detect a single candle flame from miles away on a clear, dark night. It adjusts to dim rooms and blazing sunlight within seconds. It can track a fast-moving object, read fine print, pick out a face in a crowd, but for all of that, it has a severe limitation. It can only see an extraordinarily narrow slice of the radiation that fills the universe. Everything outside that slice is invisible to us, completely undetectable. Not dim, not faint, simply gone, as if it doesn't exist at all. Visible light sits between about 400 nanometers on the violet end and about 700 nanometers on the red end. That's the range, violet to red, 400 to 700 nanometers. Outside of that window, nothing registers. Your eye receives no signal. And when you look at the full electromagnetic spectrum, the complete range of radiation that exists in the universe, visible light is a narrow band crammed into one small region. Radio waves can stretch for kilometers in wavelength. Microwaves measure in millimeters. Infrared sits just below red. Ultraviolet sits just above violet. Then come X-rays, and then gamma rays, with wavelengths smaller than a single atom. Our visible window covers a tiny fraction of all of that. It's not even close to half. It's not even close to a tenth. It's a sliver so small that calling it narrow feels like an understatement. Now think about what that means for the night sky. The universe isn't broadcasting only invisible light, it's sending out radiation across the entire spectrum, constantly, from every direction. Radio waves stream through you right now from pulsars thousands of light years away. Microwaves fill every point in space, the remnant glow of the Big Bang itself. Infrared radiation pours from warm gas clouds and distant galaxies. Ultraviolet light blazes off the surfaces of young, hot stars. X-rays pulse from the collapsed cores of dead stars and from massive black holes consuming material at the centers of galaxies. Gamma rays burst from cataclysmic events so energetic that nothing in everyday life comes close to them. All of this is real. All of it is happening right now. None of it is visible to you. Here's a useful way to think about it. Imagine you're standing in a city at night with a radio receiver, but the receiver is locked permanently to one station. You hear that one station. Everything else is silence. You might start to believe the airwaves are mostly empty, but the city has hundreds of stations broadcasting simultaneously. Music, news, sports, emergency frequencies, aviation channels, weather bands, all of it overlapping in the air around you. Your receiver just can't pick any of it up. You're not hearing silence. You're hearing the limits of your equipment. That's the night sky. Your eyes are locked to one channel. The universe is broadcasting on hundreds. If you could see microwaves, the sky would never go dark. In every direction, from every point in space, the cosmic microwave background would fill your entire field of view with a faint, uniform glow. It would be everywhere at once, not bright enough to cast shadows, but unmistakably there, washing across the entire sky without a single gap. The dark patches between stars wouldn't be dark at all. They'd be lit with this ancient light, this relic radiation from 380,000 years after the Big Bang, stretched and cooled but still present, still filling the universe, still arriving at your eyes from every direction. If you could see radio waves, the sky would look completely different again. Pulsars scattered throughout the Milky Way would pulse on and off with almost mechanical regularity. Giant radio galaxies at enormous distances would sprawl across huge portions of the sky, far larger in apparent size than the full moon. The center of the Milky Way would glow intensely, supernova remnants. The expanding shells of gas left behind by exploded stars would light up like enormous glowing rings spread across the sky. You'd have no idea you were looking at the same universe. It would seem like an entirely different place. If you could see X-rays, something else entirely would emerge. The hot gas trapped between galaxies and massive galaxy clusters would blaze with X-ray emission. These clusters contain gas heated to tens of millions of degrees, and at those temperatures, objects glow in X-rays the way hot metal glows red. They're invisible to us entirely, but to an X-ray eye, they'd be among the brightest objects in the sky. Dying stars, neutron stars, and stellar black holes, pulling gas from companion stars, would flare brilliantly. The sky would be active and violent in ways that look nothing like the quiet dark we're used to seeing. So why are our eyes the way they are? The answer is evolution. Our eyes didn't develop to observe the cosmos. They developed to help us survive on the surface of a particular planet, orbiting a particular star, under a particular atmosphere. The sun pours out most of its energy in the visible range. That's not a coincidence. Our atmosphere filters out much of the ultraviolet, the X-rays, the gamma rays from above. The light that reaches the ground most effectively, the light that was available and useful to early living creatures on Earth, falls mostly in that 400 to 700 nanometer window. Evolution built detectors tuned to the available signal, and that was the visible spectrum. It was an excellent adaptation for finding food, avoiding predators, navigating terrain, identifying members of our own species, but it was never designed for looking at stars. Our eyes evolved for survival at ground level, not for taking inventory of the electromagnetic output of the universe. The darkness we perceive when we look at the night sky is, in a very real sense, a biological accident. We happen to be sensitive to a narrow range. Everything outside it is invisible, not because it isn't there, but because we were never built to detect it. This is one of the reasons astronomers rely on so many different types of telescopes. Optical telescopes see what our eyes can see, just more of it and farther away. But radio telescopes detect wavelengths from centimeters to meters. Infrared observatories pick up heat radiation from objects too cool or too distant to glow in visible light. X-ray telescopes in orbit above the atmosphere map the hot, violent universe of collapsed stars and superheated gas. Each type of telescope opens a window our eyes can't. Each one reveals a universe that looks nothing like the one we see with our naked eye looking up on a clear night. What all of these telescopes confirm is the same thing. The universe is not dark, it is filled with radiation at every wavelength. The darkness of the night sky is a feature of human biology, not a feature of the cosmos. Strip away the limitations of our eyes and replace them with instruments sensitive to the full spectrum, and the sky would never be dark. It would be lit from every direction, in every wavelength, with radiation from sources near and distant, ancient and recent, violent and gentle. The universe is loud with radiation in every direction. We're just not built to hear most of it. It's worth dwelling on just how many stars there are, because the number seems like it should settle the question. The observable universe contains roughly 2 septillion stars. That's a 2 followed by 24 zeros. 2 trillion trillion. There's no clean way to visualize that number. It exceeds the number of grains of sand on every beach and desert on Earth. It exceeds the number of atoms in a human body. It's a count so enormous that it almost loops back around to meaningless. And yet, from a dark field, observing the celestial sphere above you, you see a few thousand stars with the naked eye. Maybe a few thousand, not 2 septillion, not even close. So where is all that light? Start with something closer to home. The Milky Way alone contains somewhere between 100 and 400 billion stars. That's our galaxy. Our neighborhood, 100 billion stars burning inside a disk roughly 100,000 light-years across. If you spread those stars evenly across that volume, you get a sense of how thinly scattered they actually are. Take a sphere just 10 light-years across, centered on Earth. Inside that sphere, you'll find roughly a dozen stars. A dozen. Not thousands, not millions. About 12 stars in a bubble 10 light-years wide. Think about what 10 light-years means. Light travels at 186,000 miles per second. In a single year, it covers nearly 6 trillion miles. 10 light-years is 60 trillion miles. A sphere 60 trillion miles across contains roughly 12 stars. That's how empty space actually is at the scale we live in. Now here's where the math starts working against the bright sky. The inverse square law governs how light behaves across distance. When light radiates outward from a source, it spreads in all directions simultaneously. It doesn't thin out gradually. It thins out geometrically. Double the distance from a star, and its light spreads across 4 times the area. The same energy, covering 4 times the surface. That makes the star appear 4 times dimmer. Triple the distance, and it's 9 times dimmer. 10 times the distance, and it's 100 times dimmer. Not 10 times, 100 times. The brightness of a star doesn't fall off in a straight line. It drops with the square of the distance. This is a ruthless mathematical relationship, and it applies to every star in the universe without exception. Let's put that in perspective with something real. Our nearest stellar neighbor beyond the Sun is Proxima Centauri, sitting about 4.2 light-years away. It's a red dwarf, too faint to see without a telescope even at that distance. Now imagine a star identical to our Sun placed at the distance of the galactic center, roughly 26,000 light-years away. A star 10 times farther looks 100 times dimmer. A star 1,000 times farther looks 1,000,000 times dimmer. A star 26,000 times farther than our Sun, because our Sun is roughly 1 light-year from itself in these comparisons, becomes so dim that no human eye could ever detect it. It's still burning. It's still pouring out energy. But across that distance, the inverse square law has reduced its apparent brightness to essentially nothing as far as our eyes are concerned. Now scale this outward. The Andromeda Galaxy sits about 2.5 million light-years away. It contains roughly 1 trillion stars, 1 trillion. And from Earth, it appears as a faint smudge in the sky, barely visible on a dark night, covering a region of sky larger than the full moon but so dim that most people have never noticed it. 1 trillion stars at 2.5 million light-years, and the combined result is a faint smear. That should tell you something important. Distance is winning. Distance and the inverse square law together are draining starlight before it reaches us. Consider also the temporal dimension underlying this problem carefully. A star's contribution to our night sky depends not just on brightness and distance, but on when it was actually shining. If a star exploded 5 billion years ago, its light may have already passed Earth or might still be traveling from distant regions. This temporal mismatch means we observe the universe at different historical stages when looking at different distances. The most distant objects are also the oldest. Many of the brightest stars that shone back then have since expired. This creates a fundamental asymmetry in what reaches our eyes. The universe's age of 13.8 billion years acts as a hard limit on how far back light could travel to reach us today. Go further. Push out to the galaxies detected by the Hubble Space Telescope, billions of light-years away. Each one of those tiny smudges in deep field images contains hundreds of billions of stars. But stretched across billions of light-years, squared in the inverse square calculation, those stars contribute almost nothing to the brightness of our sky. They are there, they are real, but their light has been diluted to the point where our eyes register darkness, not brightness, when we look in that direction. And here's something most people don't stop to consider. Not all of those 2 septillion stars are still burning. Massive stars burn fast and die young. A star born with many times the mass of our Sunday may fuse through its hydrogen fuel in only a few million years. A few million years sounds like a long time, but the universe is 13.8 billion years old. Many of the most massive, most luminous stars that ever existed burned out billions of years ago. They exploded in supernova, scattered their material across space, and went dark long before the light from their deaths even finished traveling toward us in some cases. The patches of sky they might have illuminated are dark now, not because nothing was ever there, but because what was there has already exhausted itself. Our own sun, a medium-sized star, will burn for about 10 billion years total. It's roughly halfway through that lifespan now. But the most brilliant stars, the ones that would contribute the most light, are precisely the ones that don't last. Luminosity and lifespan are inversely related in stellar physics. The brighter the star, the faster it burns through its fuel. So the universe's most powerful light sources are also its most temporary. This is not a coincidence. It's a consequence of the physics of nuclear fusion and gravity. And it means the sky loses some of its most intense contributors over time. The stellar density argument cuts deep when you work through it carefully. Even if you could add up every photon from every star in the observable universe and aim all of it toward Earth, the inverse square law applied to the actual distances involved means the total arriving flux doesn't produce a bright sky. Astronomers have run these calculations. They show that the total background brightness contributed by all stars in the observable universe, accounting for their distances and distributions, is far below the brightness of a stellar surface. It's not a rounding error. The sky should be dark, and it is, and the math agrees. But here's what makes this even more striking. Even if you removed the inverse square law problem somehow, even if you could magically deliver all that starlight to Earth without loss, you'd still run into the other barriers we've already covered. The finite age of the universe means light from the most distant stars hasn't arrived yet. The expansion of the universe means the light that has arrived from very distant sources has been stretched into infrared and microwave wavelengths our eyes can't detect. The stars that burned brightest are already dead. Every solution you might propose runs into another wall. The number 2 septillion sounds like it should overwhelm all objections. It sounds like more than enough stars to light up a sky, but number alone doesn't determine brightness. Distance does. Time does. The spectrum the light arrives in does. The lifespan of the source does. Each of these factors chips away at that enormous count until what arrives at your eye from the vast majority of directions you could look is nothing. Or rather, nothing visible. Add up all of it. The inverse square law, the finite age, the expansion, the death of massive stars, and the math simply doesn't produce a bright sky. When astronomers talk about the observable universe, they mean something specific. They don't mean the entire universe. They mean the portion of it from which light has actually had time to reach us. That distinction matters enormously, and it goes straight to the heart of why the night sky is dark. Think about what the observable universe actually is. It's a sphere. Earth sits at the center. The boundary of that sphere marks the farthest distance from which light could have traveled to us in the 13.8 billion years since the universe began. Anything inside that sphere we can at least in principle detect. Anything outside it we cannot. Not because there's nothing there, because the light from whatever is out there hasn't arrived yet. Here's where it gets strange. You might expect the radius of the observable universe to be 13.8 billion light-years. That would make sense if the universe were sitting still. But the universe isn't sitting still. It's expanding. It has been expanding the entire time that light has been traveling across it. So while a photon was making its long journey toward us, the space it was crossing was stretching. The object that emitted that photon was being carried further away by the expansion of space itself. By the time that light reaches our telescopes, the source is far more distant than it was when the light first departed. The result is that the observable universe has a radius of about 46 billion light-years, not 13.8 billion, 46 billion. That's the current distance to the most remote objects whose light we've managed to detect. The light took 13.8 billion years to reach us, but during those 13.8 billion years, the universe stretched so dramatically that the source is now roughly 46 billion light-years away. Space expanded while the light was in transit. That's not a trick of language. That's what actually happened. Let me put that in perspective. The diameter of the entire observable universe is about 93 billion light-years across. If you tried to cross it at the speed of light, it would take you 93 billion years. The universe is only 13.8 billion years old. It would take you nearly 7 times the current age of the universe just to travel from one side of the observable universe to the other. And the observable universe is only the part we can see. This disparity between age and size illustrates something critical. Expansion is powerful. It doesn't just move objects apart, it stretches the very fabric connecting them, fundamentally rewriting what's possible in terms of distance and time. Now consider what lies beyond that boundary. Not nothing. That's the crucial point. The universe almost certainly continues past the edge of what we can observe. In fact, most cosmologists believe the full universe is vastly larger than the observable portion. Some models suggest it extends for distances so enormous that the number of zeros you'd need to write them down would fill a page. A few models suggest the full universe may be infinite. We genuinely don't know. What we do know is that our observable bubble, as staggeringly large as it is, represents only a fraction of what exists. The expansion that stretched the observable universe to 93 billion light-years in diameter has been operating in all directions simultaneously, carrying regions of space beyond our horizon into realms we'll never access. Beyond our cosmic horizon, there are almost certainly galaxies. Billions of them, possibly trillions, stars burning, planets orbiting, all of it invisible to us. Not because anything is hiding it, but because the light from those objects hasn't completed its journey. It left those stars long ago. It's been traveling toward us this entire time, but the universe is so large and those sources are so remote that the light simply hasn't arrived. In some cases, it may never arrive. This is one of the most unsettling ideas in all of cosmology. There are places in the universe that we will never see, not because our telescopes aren't powerful enough, not because there's something blocking our view, but because physics itself sets a hard limit on what information can reach us. The speed of light is finite. The age of the universe is finite. Multiply one by the other, and you get a boundary. Outside that boundary, the universe keeps going. We just can't access it. Think about standing on a ship in the middle of the ocean. You can see to the horizon, maybe 15 or 20 miles in every direction. Beyond the horizon, the ocean continues. Other ships are out there, islands exist, but from where you're standing, you cannot see them. The curvature of Earth puts them permanently out of view. You know the ocean doesn't end at the horizon. The horizon is just the limit of your vantage point. The observable universe works the same way. The edge of it isn't a wall. There's no boundary where space suddenly ends and something else begins. The edge is simply the farthest point from which light has had time to reach us. Step outside that boundary, and you'd find more space, more galaxies, more stars. The universe almost certainly continues without interruption. But from Earth, the horizon is fixed. We cannot see past it. In fact, that horizon is moving outward even as we watch, because light from slightly more distant sources arrives every moment, adding incrementally to what we know. And here's something worth sitting with. The light that's just now arriving from the most distant objects we can detect left those sources when the universe was extremely young. Those objects may not even exist anymore in their original form. The galaxies we're seeing at the very edge of the observable universe are shown to us as they appeared over 13 billion years ago. They were young. They were forming. Many of them have since merged with other galaxies. Their stars have lived and died. What's out there now is completely different from what we see. We're looking at history, not at the present state of the cosmos. This temporal displacement matters profoundly. We can never see the current state of the distant universe, only its ancient past, because the light connecting us to it takes so long to arrive. That has a direct consequence for the darkness question. Beyond the edge of the observable universe, there may be countless stars shining right now, but none of that light has reached us. The photons those stars are emitting today are traveling toward us at the speed of light. Depending on how far those stars are and how fast the universe is expanding, some of that light will reach us eventually, some will not. But right now, in this moment, Looking out at the night sky, we see only what's arrived. Everything else registers as darkness, and the observable universe, for all its staggering scale, doesn't fill every line of sight with a star. We've established that. The inverse square law dims distant light. The finite age of the universe cuts off distant sources. Expansion redshifts their light out of the visible range. Even within the 93 billion light-year bubble we can observe, the math doesn't produce a sky full of light. Add the inaccessible regions beyond the horizon, and the case for darkness only gets stronger. What makes this remarkable is that the observable universe is already almost incomprehensibly vast. Roughly 2 trillion galaxies exist within it. 2 trillion. Each one containing hundreds of billions of stars. And still the sky is dark. Still the lines of sight mostly terminate in nothing our eyes can register. The observable universe is full of matter and energy and light, and it still produces a dark night sky. That tells you something profound about how space works. The darkness between the stars isn't empty space waiting to be filled. It's the signature of a universe with a finite age, a universe that's been expanding, a universe so large that even its visible portion contains regions from which light hasn't completed its journey. Beyond that visible portion, the universe continues, indifferent to the horizon that limits our view. The ocean continues beyond the horizon. You just can't see it from where you're standing. There's something else, something that makes the darkness of space feel less like a static condition and more like a process. The expansion of the universe isn't just a fact about the past. It's happening right now, and it isn't happening at a steady rate. It's accelerating. The universe is expanding faster today than it was 1 billion years ago. It will expand faster tomorrow than it does today. That might sound like a minor technical detail. It isn't. It changes everything about what we can see, what we'll ever be able to see, and what future observers will be able to see when they look up at the night sky. The darkness of space, it turns out, is not a fixed thing. It's growing. The discovery that the expansion is accelerating came in 1998. 2 separate teams of astronomers were studying distant supernovae. These explosions are useful because they all reach roughly the same peak brightness, which means astronomers can use them as distance markers. What the teams found surprised everyone. The most distant supernovae were dimmer than expected. They were farther away than they should have been. That meant the universe wasn't just expanding, it was expanding faster than before. Something was pushing it. That something is what we now call dark energy. We don't know what it is. We know it exists. We know it makes up about 68% of everything in the universe, and we know it's winning. Here's what acceleration means for the darkness of space. Every galaxy beyond our local group is moving away from us. The further away it is, the faster it recedes. That's been true since Edwin Hubble first measured it. But with acceleration, the recession speeds increase over time. Galaxies that are moving away from us today will be moving away even faster in 1 million years, in 1 billion years, in 1 trillion years. At some point, certain galaxies will be receding faster than light can travel toward us. Not because anything is moving through space faster than light. That's still impossible. But space itself is expanding between us and those galaxies. The light those galaxies emit will never close the gap. It'll spend billions of years traveling toward us and never arrive. Those galaxies will simply vanish. Think about what that means. Right now, we can observe roughly 2 trillion galaxies. 2 trillion. That's the current count of galaxies within our observable universe. Each one of those galaxies contains hundreds of billions of stars, and we can detect them. We can study them. We can measure their distance, their composition, their age. But that number is not fixed. It's shrinking. Galaxies at the far edge of our observable universe are already close to the threshold where their light becomes undetectable. Some may have already crossed it. The horizon isn't static, it's closing in. In the very far future, things get much starker. Cosmologists have worked out roughly what the sky will look like in 1 trillion years, assuming the acceleration continues. The answer is sobering. Most of the 2 trillion galaxies we see today will have redshifted completely out of view. Their light won't just be faint. It won't exist for us at all. It'll have been stretched beyond any wavelength that any instrument could detect. The galaxies will still be there. They'll still contain stars, but they'll be invisible, sealed behind a horizon we can never cross. They'll have been erased from the observable universe, not by destruction, but by distance and expansion. What remains visible, according to those estimates, is our own local group. The Milky Way, Andromeda, and a few dozen smaller satellite galaxies bound to us by gravity. Gravity can hold nearby structures together, even as the universe expands around them. The local group won't be pulled apart. It'll actually be pulled closer together over time, eventually merging into a single massive galaxy. But everything beyond it, the Virgo cluster, the hundreds of galaxy clusters we currently observe, the vast cosmic web of filaments and superclusters, all of it will retreat past the horizon, gone. The night sky will have stars, but it won't have galaxies. The universe that future observers see will look nothing like the one we see now. Here's what makes this genuinely strange. Those future observers won't necessarily know what they're missing. They'll look out at their sky and see the local group. They'll see stars. They'll see a night sky that still looks rich to them because it's all they have. They won't see an absence where other galaxies used to be. They won't have any record of the 2 trillion galaxies we can count today unless they inherit that record somehow. The evidence that would let them reconstruct the large-scale structure of the universe, the redshifts of distant galaxies, the pattern of the cosmic web, will have vanished. The universe will have hidden its own history. We're living through a window when that evidence is still available, and that's one of the more unsettling implications of dark energy. Not just that space is dark, but that it's becoming harder to understand. We happen to exist at a moment when the observable universe is about as information-rich as it will ever be. The cosmic microwave background is still detectable. Distant galaxies are still within reach of our telescopes. The structure of the universe is still legible. In the deep future, none of that will be true. Future civilizations, if they exist, will have access to far less of the universe's story. They'll be like scientists trying to reconstruct an entire library from a single shelf of books. The acceleration also puts a fixed limit on how much of the universe we will ever see, even given infinite time. You might expect that if we just waited long enough, we'd eventually receive light from more and more distant objects. That's not how it works under accelerating expansion. There's a boundary, called the cosmic event horizon, beyond which light emitted today will never reach us, no matter how long we wait. That boundary sits at roughly 16 billion light-years from Earth. Anything emitting light beyond that distance right now is beyond our reach, permanently. The observable universe isn't just a snapshot, it's a ceiling, and dark energy set that ceiling. The implications of this cosmic event horizon are profound. We are not merely limited by the age of the universe or by light's speed through space. We face a deeper constraint rooted in the accelerating expansion of space itself. Every second that passes, the horizon shifts further away, yet the galaxies beyond it recede faster still. The mathematics is asymmetrical and unforgiving. Distance wins. For any galaxy currently beyond that event horizon, there exists nothing we could do that would ever permit us to witness it, no matter what technologies we develop or how patient we become. The universe has drawn a permanent boundary, that expands away from us, rendering entire regions of creation forever inaccessible to observation. So when you think about the darkness of space, add this layer. The darkness isn't just a consequence of a young universe or redshifted light, or the limits of human vision. It's also a consequence of a universe that's actively pulling itself apart. Galaxies are retreating, horizons are contracting. The window of visibility that we currently enjoy is not a permanent condition. It's a phase. It may already be past its peak. The cosmos that future observers will inherit will be darker and quieter than ours, not because the stars went out, but because the vast architecture we see today will have slipped beyond any horizon they can reach. Our descendants, if any exist trillions of years from now, will look out at a sky far emptier than ours, and they may have no way of knowing what they're missing. About 380,000 years after the Big Bang, the universe went transparent. That sentence is worth sitting with for a moment. Before that point, the universe was not see-through. It was a dense, hot plasma, a soup of electrons and protons so tightly packed and so violently energetic that light couldn't travel more than a short distance before slamming into a charged particle and scattering in a new direction. Think about trying to see through a thick fog. Light enters it and immediately gets bounced around, redirected, diffused. The early universe was something like that, except far hotter and far denser than any fog we can imagine. Light was trapped. It couldn't go anywhere useful. The entire universe was opaque. Then something changed. The universe had been expanding since the Big Bang, and that expansion was cooling things down. Temperature was dropping. After about 380,000 years, the temperature fell to roughly 3,000 degrees Celsius, still extraordinarily hot by any human standard, but cool enough for something remarkable to happen. Electrons slowed down enough to be captured by protons. Neutral hydrogen atoms formed for the first time, and when that happened, the particles that had been scattering light everywhere were suddenly gone. The universe had no more free electrons to bounce photons around. Light flooded through. Every photon that had been trapped in that plasma was suddenly free to travel in a straight line across the universe. In every direction, from every point in space, light streamed outward. And that light was brilliant. The temperature of the universe at that moment was around 3,000 degrees Celsius. That puts it in roughly the same range as the surface of a cool red star. Every direction you looked, if you could have been there, you would have been looking at something as bright as a stellar surface. Not one star, not a sky full of stars, the entire sky, every single point in every direction, glowing with the intensity of a star's surface. The universe at that moment was filled edge to edge with visible light. Astronomers call this moment recombination. The light released at this moment is what we now call the cosmic microwave background, or CMB. It's the oldest light in the universe. It's older than every star, older than every galaxy, older than every planet. It was released before any of those things existed. And here's what makes it extraordinary. That light is still here. It didn't disappear. It didn't get absorbed. It has been traveling through space for 13.8 billion years. It's still going. Right now, as you watch this, photons from that ancient fireball are passing through you. They're passing through the walls of whatever room you're in. They're coming from every direction, arriving at your location from every point in the sky. The CMB is not a historical artifact we have to dig for. It's present. It's active. It fills all of space right now, continuously. But here's what most people don't realize. That light has changed almost beyond recognition. When the CMB was released, it had a temperature of around 3,000 degrees and wavelengths in the visible and near-infrared range. It was light our eyes could have detected. But in the 13.8 billion years since, the universe has expanded enormously. And as space expands, the wavelengths of light traveling through it stretch. They get longer. A photon that started its journey as visible red light has had its wavelength stretched by a factor of roughly 1,000. It's no longer red light. It's not even infrared. It's now a microwave. The entire ancient fireball, that blinding, brilliant ocean of light that filled the universe when it first went transparent, has been stretched into the microwave part of the electromagnetic spectrum. Today, the CMB has a temperature of about 2.73 degrees above absolute zero. That's 2.73 degrees warmer than the coldest possible temperature in the universe. Almost nothing. A faint, cold whisper of what was once a roar, and our eyes cannot see microwaves. Not even close. The human eye detects wavelengths between roughly 400 and 700 nanometers. Microwaves have wavelengths measured in millimeters to centimeters, thousands of times longer. When you look at the dark patches of the night sky, the patches between stars where nothing seems to be, you are looking at space, absolutely soaked in microwave radiation from the Big Bang. Your eyes pass right through it. You register nothing. But it's there. Astronomers first detected the CMB in 1965. Arno Penzias and Robert Wilson were working with a large radio antenna in New Jersey, trying to eliminate a persistent background noise from their measurements. It was coming from every direction. It didn't matter where they pointed the antenna. They checked for equipment problems. They found pigeons nesting in the dish and cleaned it out. The noise persisted. It was the cosmic microwave background, ancient light from the beginning of the universe, arriving at their antenna from every corner of the sky. They had accidentally discovered the oldest thing we have ever detected. They won the Nobel Prize in 1978. Since then, satellites have mapped the CMB in extraordinary detail. The COBE satellite in the early 1990s confirmed that its temperature is almost perfectly uniform across the entire sky. The WMAP satellite and later the Planck satellite mapped it with increasing precision, revealing tiny temperature fluctuations, variations of about 1 part in 100,000. Those tiny variations are not random noise. They are the imprint of quantum fluctuations from the first fraction of a second after the Big Bang, stretched to cosmic scales by inflation. The seeds of every galaxy, every star, every planet that exists today were written into those fluctuations. The CMB isn't just ancient light. It's a map of where everything came from. But think about what this means for the darkness of the night sky. When you look at the space between stars, there's no visible source of light. No star, no galaxy, no nebula, just blackness. And the natural conclusion is that there's nothing there. Empty space, a vacuum, silence. But that space is filled with something. Microwave photons from 380,000 years after the Big Bang are streaming through it. They've been traveling for 13.8 billion years. They carry information about the state of the universe long before Earth existed, long before the Sun existed, long before any star in our galaxy existed. The darkness we see is not absence. It's just that what fills that space is invisible to us. If human eyes were sensitive to microwaves, if evolution had taken a different path and built us with eyes tuned to centimeter wavelengths, the night sky would glow, not with stars and dark patches between them. The entire sky would be a nearly uniform, faintly glowing surface in every direction. Every dark gap between stars would be lit up. The sky would look more like a dim, featureless dome of pale light than the star-studded black we actually see. The darkness would be gone. replaced by this ancient glow from the earliest transparent moment of the universe. We don't see it. Our biology filters it out completely. But instruments can. Radio telescopes pick it up. Microwave detectors on satellites measure it with staggering precision. And what they find is that the CMB is genuinely everywhere, not coming from one source, not concentrated in one direction, but arriving uniformly from the entire sky. That uniformity is itself a clue. It tells us that the universe at the time of recombination was almost perfectly smooth in temperature across the entire sky, which means regions that are today billions of light years apart were once in thermal contact. That fact alone drove the development of inflation theory, the idea that the very early universe expanded faster than light for a brief period, smoothing out all the temperature differences. So, the cosmic microwave background doesn't just explain part of why the sky is dark. It carries within it the deepest explanation of why the universe looks the way it does. It is the Big Bang's own light, transformed by time and expansion into something our senses cannot reach. And it fills the space between everything we can see. The darkness you see between the stars is not empty. It is soaked in ancient light from the beginning of the universe, rendered invisible by 13.8 billion years of cosmic expansion. It is worth asking what a bright night sky would actually require. Not just more stars, not just a bigger universe, something more fundamental than that. To fill every line of sight with starlight, you would need a universe that is infinitely old, perfectly static, and packed with stars that never die. Those three conditions together, remove any one of them and the math starts to break down. The sky stays dark. Think about what infinitely old actually means. Not 13.8 billion years, not a trillion years. Infinite. No beginning, no moment of creation. Just an eternal universe that has always existed and always will. In that universe, light from every star in every direction would have had infinite time to complete its journey toward you. There would be no dark patches, no regions where the light simply hasn't arrived yet. Every point in the sky would be occupied. Every direction you looked, your line of sight would terminate on a stellar surface blazing at thousands of degrees. The entire sky, horizon to horizon, in every direction above and below, would glow like the surface of a star. Not just the bright points we call stars tonight, the whole dome of the sky, solid with light. That is not a comfortable place to live. It is not a place where anything lives at all. The surface temperature of our sun is around 10,000 degrees Fahrenheit. The surface of a cooler red giant runs closer to 6,000. An infinite static universe filled with eternal stars would bathe every point in space with radiation equivalent to a stellar surface. The energy density in that environment would be catastrophic. Water doesn't exist above a few hundred degrees. Complex molecules break apart. DNA doesn't survive. The chemistry that produces life, that allows proteins to fold and cells to function and organisms to persist over time, requires a relatively narrow temperature range. A universe with a sky as bright as a star's surface provides no such range. Anywhere you go, the temperature climbs to match the radiation field surrounding you. So here's what most people don't immediately realize. The darkness of the night sky isn't just an interesting cosmological fact. It's part of the reason you exist to notice it. The conditions that keep the sky dark are the same conditions that allow complex chemistry, planets, and life. The universe has a finite age, so light from distant regions hasn't arrived. The universe is expanding, so distant light gets stretched out of the visible range. Stars are born and they die, so the supply of light sources is constantly changing rather than building up forever. Every one of those conditions that explains the darkness also creates the environment where life becomes possible. A universe bright enough to fill the sky with starlight uniformly is a universe where Earth doesn't exist, where oceans don't exist, where biology never gets started. The darkness is not a flaw in the design of the universe. It's part of the package. This isn't an argument that the universe was arranged for our benefit. It's a simpler observation than that. The kind of universe that allows life to develop is also, almost by necessity, the kind of universe that has a dark night sky. You can't really have one without the other. The finite age, the expansion, the mortality of stars, those properties are linked. They come together, and together they produce both the darkness above you and the conditions below you that make it possible to look up and ask why. Now here's where the paradox becomes something more than a puzzle about light. Olbers Paradox isn't just a question about why the sky looks the way it does. It's a question about the structure of the universe itself. And the answer, it turns out, is a description of the universe we actually live in. A universe with a beginning. A universe that grows. A universe with a history that stretches back only so far before it hits a wall. A moment before which our current understanding of physics starts to break down. Astronomers didn't always know this. For most of human history, the dominant assumption was that the universe was eternal and unchanging. Stars had always been there. The sky had always looked this way. The idea that the universe had a starting point was not obvious. It wasn't intuitive. It required evidence, and gathering that evidence took most of the 20th century. Edwin Hubble's observations in the 1920s showed that galaxies were moving away from each other. The further away, the faster the recession. That discovery implied the universe was expanding. Run the expansion backward and you arrive at a point, a moment when everything was compressed into an unimaginably dense state, the Big Bang. But here's what's remarkable. Olbers' paradox was already pointing in that direction long before Hubble made those observations, long before anyone had the tools to measure the recession of galaxies. Long before the cosmic microwave background was detected or anyone understood what it represented. The simple fact that the night sky is dark was already evidence that the universe couldn't be infinite and eternal and static. The darkness was already telling us something was wrong with that picture. Think about what that means. You don't need a spectrograph. You don't need a radio telescope. You don't need the James Webb Space Telescope or a particle accelerator or any instrument at all. You need to go outside on a clear night and notice that the sky between the stars is black. That observation alone, available to any human being who has ever lived and looked upward, is inconsistent with a universe that is infinitely old and filled with eternal stars. The darkness is the clue. It always was. Astronomers in the 1800s debated possible explanations: dust clouds, uneven distribution of stars, the possibility that the universe had edges. None of those explanations held up under scrutiny, as we've already covered. The real answer required accepting something most people at the time were not ready to accept: that the universe had not always existed in its current form, that it had a beginning, that it had been different in the past and would be different in the future. The dark sky above us is quiet confirmation of all of that. It's sitting there every night, waiting to be noticed. Heinrich Olbers didn't know he was asking a question about the Big Bang. He thought he was asking a question about stars and light and why the sky looks the way it does. But the two questions turned out to be the same question. The local observation and the cosmic truth collapsed into a single answer. The sky is dark because the universe is young, finite, and growing. And we know the universe is young, finite, and growing, partly because the sky is dark. Long before astronomers had the Big Bang model, the darkness of the night sky was already pointing toward it, the simplest observation a human can make. containing one of the deepest truths about the cosmos. Every time you look at a star, you are looking into the past, not metaphorically, not approximately, literally. The light entering your eye left that star years, decades, centuries, or billions of years ago. By the time it reaches you, the universe has moved on. What you're seeing is history. Think about what that means for something as close as the sun. The sun is about 93 million miles away. Light covers that distance in roughly 8 minutes. So the sun you see right now is the sun as it existed 8 minutes ago. If something dramatic happened to the sun at this exact moment, you wouldn't know for 8 minutes. You'd still see a perfectly normal star hanging in the sky while, in reality, something had already changed. That's a strange thing to sit with. Your experience of the sun is always slightly out of date. Now move further out. The nearest star beyond our sun is Proxima Centauri, sitting about 4.2 light-years away. The light reaching us from Proxima Centauri tonight left that star 4 years ago. 4 years. Whatever Proxima Centauri looks like right now, we have no idea. We're watching a 4-year-old broadcast. Move to Sirius, the brightest star in the night sky, and the delay jumps to about 8.5 years. Move to the stars of the Orion constellation, and you're looking hundreds of years into the past. Betelgeuse, that reddish giant marking Orion's shoulder, sits roughly 700 light-years away. The light we receive from Betelgeuse tonight left during the 1300s. When that light began its journey, the Renaissance hadn't started. There was no printing press. Nobody on Earth had any idea that light was even traveling toward them from that star. Move further still. The Andromeda Galaxy is the most distant object visible to the naked eye. It sits about 2.5 million light-years away. When you find it on a dark night, a faint smear of light in the constellation Andromeda, you are seeing that galaxy as it appeared 2.5 million years ago. Homo sapiens didn't exist yet. Our ancestors were using stone tools. The Andromeda you see tonight is an ancient image. The actual, present-day Andromeda is hidden from us completely. And that's just with your naked eye. With telescopes, the distances stretch further. The Hubble Space Telescope famously captured galaxies more than 13 billion light-years away in the Hubble Deep Field images. Those galaxies are showing us what they looked like when the universe was less than 1 billion years old. Some of those early galaxies may not even exist in their original form anymore. They may have merged. They may have transformed completely. We're looking at infant structures in a universe that is now ancient. The James Webb Space Telescope pushed even further, detecting galaxies formed just a few 100 million years after the Big Bang. The universe in those images is unrecognizable. No planets, no heavy elements, just the earliest galaxies clumped together in a cosmos that had barely begun. Here's the way to picture it. The observable universe isn't a flat map. It's a set of nested spheres around Earth. The innermost sphere shows you the very recent past, stars within a few light years. The next sphere out shows you further back, and further, until the outermost edge of what we can detect shows us the universe as it was more than 13 billion years ago. We are sitting at the center of a time machine. Every direction you look is a different depth in time. The sky isn't just a spatial map of the universe, it's a temporal one. Near things are recent, distant things are ancient. The further you look, the further back you see. This is why those dark patches matter. When you stare into a gap between visible stars, into what looks like pure emptiness, you are looking at distances so extreme that whatever exists out there is showing you a past older than most stars. Some of those dark regions do contain objects. The James Webb Telescope has found galaxies lurking in areas that appeared empty to older instruments. What looked like nothing turned out to be the very distant universe. Its light shifted and faint and invisible to previous technology. The darkness isn't absence, it's distance, and distance is time. But here's what makes this feel genuinely strange. The present state of everything beyond our solar system is completely hidden from us. Right now, in this moment, things are happening all across the universe. Stars are exploding. Galaxies are colliding. New solar systems are forming. We have no access to any of it. We can only see the messages that have already been sent, the light already traveling toward us. Everything else is silence. The universe in its current state, the way it actually is at this moment, is a picture we will never see. By the time any signal from distant events reaches us, millions or billions of years will have passed. And that cuts both ways. There are stars we can see right now that may no longer exist. Massive stars live fast and die violently. A star 10,000 light-years away that we see tonight as a stable, burning point of light may have exploded 5,000 years ago. The explosion happened. The shock wave expanded. The star is gone. But the light from that explosion is still thousands of years from reaching us. We look at it and see nothing wrong because we're watching old footage. Astronomers know this. When they talk about watching supernovae, the violent deaths of massive stars, they know they're watching something that already happened, sometimes millions of years in the past. The star died long before any human civilization existed. The light of its death is just now arriving. When it reaches Earth, we detect a sudden brightening in the sky, and we say we've witnessed a supernova. But we haven't witnessed it in any real-time sense. We've received its message. The event itself is ancient history. This is one of the most disorienting things about the scale of the universe. We feel like we are observing the cosmos. We feel like observers in the present tense. But we're really reading a collection of old letters, each one sent at a different point in the past, all arriving together in our telescopes and our eyes. The universe we see is a mosaic assembled from different moments in time, layered on top of each other and presented to us as a single sky. Somewhere out there, a star has already exploded, and we don't know it yet, because the light from that explosion hasn't finished traveling toward us. The third layer is stellar lifetimes. Stars don't burn forever. Massive stars, the brightest ones, the ones that pump out the most light, deplete their reserves in just a few million years. They explode. They go dark. Many of the stars that could theoretically illuminate certain patches of sky have already been dead for billions of years. The universe is full of remnants. White dwarfs, neutron stars, black holes. These were once sources of light. They aren't anymore. The darkness in some parts of the sky isn't because light hasn't arrived yet. It's because the source stopped broadcasting long ago. There is one more layer to this, and it is the strangest one. The stars are not going to last forever. Every star you can see tonight is burning through a finite supply of hydrogen fuel. The sun has about 5 billion years left. Some massive stars have only a few million years. And smaller, dimmer red dwarfs can burn steadily for trillions of years. But even they have limits. Given enough time, every star in the universe will exhaust its fuel and go dark. The question is just how long that takes. The number astronomers arrive at is roughly 100 trillion years. Written out, that's a 1 followed by 14 zeros. Our sun is about 4.6 billion years old. The universe itself is 13.8 billion years old. 100 trillion years dwarfs both of those numbers so completely that they almost cease to be meaningful comparisons. If the entire current age of the universe were 1 second, 100 trillion years would be over 7,000 seconds. That's nearly 2 hours. We are, cosmically speaking, moments into this story. But here's what that number means. Somewhere around 100 trillion years from now, the last star will run out of hydrogen. Fusion will stop. The light will go out. No new stars will form because the gas clouds that birth stars will have been exhausted or scattered. The universe will enter a phase cosmologists call the degenerate era. It won't be empty exactly. White dwarfs will still be out there, the collapsed remnants of stars like our sun, slowly cooling over incomprehensible timescales. Neutron stars will remain. Black holes will persist, but none of these things produce light the way a living star does. The universe will be cold and dark and quiet in a way it hasn't been since before the first stars formed. After the degenerate era comes the black hole era. The white dwarfs cool further. They fade from red to black, becoming what some call black dwarfs, objects so cold they emit almost no radiation at all. The black holes persist, slowly evaporating through a quantum process called Hawking radiation. This evaporation is extraordinarily slow. A black hole with the mass of our sun would take about 10 to the power of 67 years to evaporate fully. That number is larger than 100 trillion by so many orders of magnitude that it's essentially incomparable. Eventually, even those black holes will be gone. What remains after that is called the dark era, a cold, featureless expanse, widely separated particles drifting through an enormous and expanding void. No stars, no heat, no light of any meaningful kind. Think about that arc for a moment. The universe begins in a state of blinding, inconceivable brilliance. The Big Bang releases more energy than we have any framework to truly describe. The early universe is not dark at all. It is a hot, dense plasma, glowing everywhere at once. Light cannot even travel freely through it for the first 380,000 years because the plasma is too thick, too energetic, too opaque. When the universe finally cools enough to become transparent, that ancient light floods outward in every direction. That is the cosmic microwave background. That is the moment the universe first became something light could cross. Then comes the cosmic dark ages. This is a period that runs from about 380,000 years after the Big Bang to somewhere around 150 to 180 million years after. No stars exist yet. The universe is filled with hydrogen and helium gas, slowly cooling, slowly clumping under gravity. There is no fire anywhere, no fusion. The only light is the fading glow of that ancient background radiation, steadily cooling, steadily dimming. The universe is dark in a way it will eventually be dark again at the end. Then the first stars ignite. Massive, brilliant, short-lived giants. Some of them are hundreds of times the mass of our sun. They burn ferociously and die quickly, but they end the darkness. They flood the universe with ultraviolet radiation. They forge the first heavy elements inside their cores. When they die in supernovae, they scatter those elements into space, seeding the next generation of stars, and then the next, and then the next. Each generation builds on what the last left behind. We are inside that sequence right now. The universe is about 13.8 billion years old, and star formation is still happening. New stars are being born in nebulae right now, at this moment. The Milky Way produces a few new stars every year. Other galaxies are doing the same. We are not near the end of the stellar era. We're not even in the middle. Star formation began in earnest only a few 100 million years after the Big Bang and has been declining slowly since its peak about 10 billion years ago. But stars are still forming. We live in an era of starlight, and that is genuinely unusual in the context of everything that has happened and everything that will happen. The total span of the stellar era is roughly 100 trillion years. We are currently about 13.8 billion years into it. That is roughly 0.014% of the way through. We are extraordinarily early. The universe is young. The stars are young. Most of the star formation that will ever occur in the universe's future hasn't happened yet. Most of the red dwarf stars that will ever slowly burn their hydrogen haven't even begun their lives. We are in the opening moments of an era of starlight that has barely started, but it will end. Red dwarfs will outlast everything. They're the most common type of star, and the most miserly with their fuel. Stars like Proxima Centauri, the closest star to our Sun, could burn steadily for 4 to 8 trillion years. Long after our Sun is gone, long after every Sun-like star in every galaxy has faded, the red dwarfs will still be burning dimly. Little red embers scattered across an expanding void. The last stars in the universe will almost certainly be red dwarfs, cooling so slowly that their light shifts from red toward infrared, and finally into wavelengths no human eye could detect. They won't wink out suddenly. They'll just gradually fade below any threshold of visibility, and the darkness will settle in without any clear moment of finality. Our descendants, if any exist that far into the future, will have watched that happen. They will have seen the stars thin out. They will have watched galaxies go dark one region at a time. They will have understood in a way we can only calculate what it means for the universe to age past its capacity to produce light. We can do the math now. We know the sequence. We just can't feel it the way a civilization living through it would feel it. There is something strange about sitting inside this moment and knowing all of that. The night sky looks the way it does, dark with scattered points of light, because the universe is finite in age and expanding and filled with stars that haven't lived forever and won't live forever. That darkness is not a permanent backdrop. It's a snapshot. It looked different in the past. It will look different in the future. Astronomers in 100 trillion years, if there are any, will look out at a sky darker than ours. They will have to work harder to explain the physics of a dying universe than we work to explain our living one. And astronomers who could have existed 200 million years after the Big Bang, in the heart of the cosmic dark ages, would have looked out at a sky with no stars at all, nothing to see, no light except the fading microwave glow of the Big Bang itself. They would have had no way of knowing that 13 billion more years of starlight were coming. We are between two darknesses. Before us was the dark age of the early universe. Ahead of us, eventually, is the permanent dark of the exhausted universe. In between is this: a sky with stars, a sun that rises, a galaxy full of burning fusion, a universe still young enough to be luminous. That is where we are. That is when we are. The darkness isn't nothing. It is time and distance, and the age of the universe, and the limits of human eyes, and the whole long history of light and matter compressed into a black sky and a handful of visible stars.